Welcome to the second part of Review Lecture 6-2. If you have not yet viewed Part A, please do that before coming here. Otherwise, you won't know what the heck's going on. Okay, this is about magnetic fields and current. Continued. We're just going to go continue this. Okay, now we were just about ready to start talking about coils. Or later we call them inductances. Anyway, solenoids and toroids. A solenoid is a long, tightly wound heliocoil of wires. So in other words, it looks like a slinky. The solenoid's magnetic field is a vector sum of the fields produced by the individual turns or windings that make up the solenoid. For points very close to a turn, the wire will behave magnetically, almost like a long, straight wire, and the lines of magnetic field there are basically concentric circles. Now, the lower figure suggests that the field lines have a tendency to cancel between the adjacent turns. You can see this one's going this way and that one's going that way, so they have a tendency to cancel out. It also suggests that points inside the solenoid, down the central axis of the solenoid, reasonably far from the wire, the magnetic field is approximately parallel to the central solenoid axis. This is very much like a bar magnet, and it's kind of the equivalent of a capacitor. Where a capacitor stores its energy in electric fields, a solenoid stores its energy in magnetic fields. Okay, now if you're a Physics 222 student or you have calculus, okay, you should be going to this slide here. If you are a Physics 122 student that is non-calculus based, please go to slide number 8. We have Ampere's law. We're going to use that to calculate the magnetic field of a solenoid, again, for calculus-based students. We're going to apply Ampere's law. The integral of B dot ds equals mu naught I enclosed to the ideal solenoid where B is uniform within the solenoid and 0 outside of it. And we're going to use a rectangular Amperian loop, A, B, C, D, A. And we're going to write Ampere's law, the integral of B dot ds is the sum of 4 integrals. This one, that one, and that one. Okay, so we sum these all up. It is from A to B of B dot ds, B to C of B dot d, etc., all the way down back to the last one, which of course is D to A. You always have to complete the loop. People usually forget this one. I look at that going, why am I doing that twice? No, it actually is you have to complete the loop. Back to the starting point. So now we can do each one of these. The integral of B dot ds in this case is just B times this straight line here, okay? So it's B times SAB times the cosine of theta AB. And then we have similarly, it's the same equation. All we're doing is applying to different parts of this closed loop. So it's B, SBC, cosine theta, BC, etc., all the way down to the last one, B, SDA, cosine theta, DA. Now, most of these drop out. The only one that does not drop out is this one, A to B, because this, of course, this angle is 0. It's the angle between B and this part of the loop, so it's 0. This one is 90 degrees, so it drops out. This one, there's no magnetic field outside loop, so BCD is 0, so that one drops out. And again, this one is perpendicular to magnetic field. The cosine of 270, of course, is 0. So the only one that sticks around is this first part of the loop, A to B. So the integral of B dot ds is just BAB times h times the cosine of theta of 0 squared. And h, of course, is this distance, the length of the loop, the long side of the loop in this case. So the integral B dot ds equals BH, and that equals mu naught I enclosed by Ampere's law. So the net current I enclosed encircled by the Amperian loop is not the same as the current through the solenoid's windings, because the loops, you see that there's multiple points where the current passes through the loop. We're going to let n be the number of turns per unit length of the solenoid, and then the loop will enclose n times h turns. So I enclosed is just I and h. Thus, for an ideal solenoid, we're going to exclude the n's. The magnetic field magnitude can be defined as pH equals mu naught I enclosed, then equals mu naught I times n times h. So then the magnetic field of a solenoid is B equals mu naught I times n. Now this assumes the solenoid is long relative to its diameter and it's tightly coiled with very little space between the wires of its coils. So in other words, the wires are touching each other, maybe only separated by the length of their insulation, which would probably be something very thin made out of lacquer. Typically, they have like transformer wire, which is a copper wire that's covered with a very thin plastic coating or lacquer coating. If you are a Physics 122 student, in other words, you don't have calculus, you should be here. We're going to apply Ampere's law of the integral of B dot ds, or in this case, the summation over the entire loop, B parallel delta L equals mu naught I enclosed to the ideal solenoid, where B is uniform within the solenoid and 0 outside of it. We're going to use this rectangular Amperian loop, and that will be A, B, C, D, A. We're going to write this integral as the sum of 4 parts, or the summation is the sum of 4 parts, one for each loop segment. In other words, one for each side of this rectangle. Then we just sum them up. We have B parallel delta L for segment AB. We have B parallel delta L for BC, so on, all the way around the last one. You have to close the loop, B parallel delta L dA. Now we can rewrite that as BAB, H times the cosine of 0 degrees. Where does the 0 degrees come from? So it's the angle between the magnetic field lines and that part of the loop, and it has to be 0 degrees. Now BC, for this part, that will be the cosine of 90 degrees, so it's going to drop out. Outside the solenoid, the magnetic field is 0, so that's going to drop out. This last one drops out because the cosine of 270 degrees is also 0. So the only one that remains is this first one. So the integral of B dot ds, or the summation of B dot ds, equals B times H, and that equals mu naught I enclosed. Okay, so the net current encircled by the Amperian loop is not the same as the current I in the solenoid windings, because the windings will pass more than once through the loop. So we have each one of these dots here is a current coming towards you in a winding. We're going to let n be the number of turns per unit length of the solenoid. Then the loop will enclose as n times h turns, and I enclose as I and h. For an ideal solenoid, we exclude the n's. The magnetic field magnitude can be defined as B times H equals mu naught I enclosed equals mu naught I n H. Then the magnetic field of a solenoid is B equals mu naught I times n. Now this assumes the solenoid is long relative to its diameter and is tightly coiled with very little space between the wires of its coil. And that's typical for most solenoids. They wind these as tightly together as possible. Okay, the magnetic field of a solenoid with material inside of its coil. The general formula, if you put a material of magnetic permeability, a mu m, inside the coil, is that B equals mu m times I times n. This is like putting dielectric inside of a capacitor. Most materials don't have much of an effect, but iron and other ferromagnetic types can increase B by more than 1,000 times. Now remember, the diamagnetic material didn't do much more than 300. Yeah, there's also something else about this. Unlike the dielectric in a capacitor, mu m is also dependent upon the magnetic field strength inside the coil. The strength of the magnetic field B only depends upon the current I flowing through the wire and the number of coils N per unit length and the material inside the coils. The field strength does not depend upon the solenoid diameter or the length of the solenoid, assuming that the same number of coils per unit length for multiple lengths. Solenoids are a very practical way of creating uniform magnetic fields, just like capacitors create uniform electric fields. Solenoids store energy in the magnetic field, just as the capacitor stored energy in the electric field. So they're pretty cool. Solenoids, remember, capacitors came in different shapes. We had parallel plate, we had spherical, we had cylindrical. Well, solenoids do too. And the most common types are the long cylindrical version. But you can take that cylindrical one and bend it into a toroid. Okay, this is for Physics 222 students. That is calculus-based. If you are not calculus-based, please go to the next slide, which will be slide number 12. A toroid is a hollow solenoid that has been curved until its two ends meet, forming a sort of hollow bracelet. Kind of looks like a donut with wire wrapped around it. The magnetic field B inside the toroid body can be determined using Ampere's law and the toroid symmetry. The lines of magnetic field form concentric circles inside the toroid, directed as shown in the lower figure. Now we're going to choose a concentric circle radius r as an Amperian loop to take advantage of the symmetry. And we're going to transverse it in the clockwise direction. Why clockwise? Because the current in these windings inside the Amperian loop is into the page. If you put your thumb of your right hand into the page, your fingers curl clockwise. So that's the direction we're going to go around this. So we take B dot ds and we can pull the B outside because it's a constant because of the way we set this up. So it's B times the integral from 0 to 2 pi r, that's the circumference, ds. So it becomes B times 2 pi r equals mu naught I times n. And we can solve this for B equals mu naught I n over 2 pi times 1 over r. I is the current in the toroid windings and is positive for those windings inside the Amperian loop, and n is the total number of turns. Now, the magnetic field is not constant. Inside the toroid body, it is proportional to 1 over r. In the donut hole and outside the toroid body, it's 0. If you are a Physics 122 student or you don't have calculus, this is where you should go. A toroid is a hollow solenoid that has been curved into its two ends meet, forming a sort of hollow bracelet. Magnetic field B inside the toroid body can be determined using Ampere's law on the toroid symmetry. The lines of magnetic field form concentric circles inside the toroid, directed as shown in the lower figure. We're going to choose one of these concentric circles, one of radius little r, as an Amperian loop, and transverse it in the clockwise direction, yielding the sum. We're going to pull out, because the magnetic field is constant along this circumference of the circle, we can pull the magnetic field out in front of the summation sign. So we can say B parallel times the sum of all the delta L here, and that's just the circumference, has to equal B times 2 pi r, the circumference of the circle, and that has to equal, by Ampere's law, mu naught I times n. So then we can solve this for B. B equals mu naught I times n over 2 pi times 1 over r. I is the current in the toroid windings, and is positive for those windings enclosed by the Amperian loop, and n is the total number of turns in the toroid. Now the magnetic field, notice the 1 over r. The magnetic field is not constant. Inside the toroid body is proportional to 1 over r. So it depends on where you are inside the toroid. The magnetic field in the donut hole is 0 for an ideal toroid, and it's 0 also outside for an ideal toroid. So what's the difference between a toroid and a solenoid? A solenoid is a straight coil of uniform turns per unit length. B is constant over the cross-section. It's 0 outside. It's independent of radius. Toroid is a bent solenoid in the form of a ring, sort of looks like a donut with wires wrapped around it. B varies over the cross-section is proportional to 1 over r. It's 0 outside and 0 inside the hole, and it depends upon the radius, inversely dependent upon the radius. So here we have another example. A solenoid has a length L of 1.23 meters and inner diameter of 3.55 centimeters. It carries a current of 5.57 amps. It consists of 5 close-packed layers, each with 850 turns along length L. What is B as its center? Now, the first thing I notice is here, this is definitely a long, skinny solenoid, so we can assume this one's ideal. The physics of this is a magnetic field of a solenoid. Its length is much greater than its diameter. The coil is tightly packed, so we're going to be okay to use the solenoid formula because it's an ideal solenoid. First thing you do, you write down the knowns and unknowns. L is 1.23 meters. Convert everything to SI. Definitely do that. I see lots of problems on homework problems because people don't convert to SI, or they leave units off entirely, and then they forget to convert to SI because they don't check the units. And that's deadly in these classes. Imagine what that's going to do to you on a test. Yeah, that should be enough to scare you straight. D equals 0.0355 meters. The current is 5.57 amps, and N is 5 times 850 turns. That's 5 layers of 850 turns each. The formula is B equals mu naught I times little n, and little n equals big N divided by L. Okay, so we solve this. B equals mu naught I times little n, or equals mu naught I big N divided by L. Now we can put our numbers in. Our mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. Our current is 5.57 amps. The number of turns is 5 times 850, and the length is 1.23 meters. The magnetic field is 2.42 times 10 to the minus 2 Tesla. That's a pretty good magnetic field. Okay, the magnetic field produced by a current-carrying coil, which is a magnetic dipole, at a point P, located a large distance z along the coil's perpendicular central axis, is parallel to the axis, and is given by B equals mu naught over 2 times I times big R squared over Z cubed. Now, for vector format, vector B equals mu naught over 2 pi times vector mu divided by Z cubed. Vector mu is the dipole moment of the coil, and mu equals NIA, where N is the number of turns in the coil, I is the current in the turns, and A is the area. This equation applies only when Z is much greater than the radius of the coil. In other words, you're far away from this. Otherwise, you have to use B of Z equals mu naught over 2 times I times big R squared divided by the 3/2 power of the quantity big R squared plus Z squared. Or vector B equals mu naught over 2 pi times vector mu divided by the 3/2 power of the quantity big R squared plus Z squared. The dipole, of course, generates its own magnetic field. This allows it to experience a torque when it's placed in an external magnetic field because the two magnetic fields interact with each other. The torque will cause the dipole to align with the external magnetic field so the dipole's magnetic moment aligns with the external field. The right-hand rule for determining the direction of the dipole moment is to take your fingers and put them in the direction of the current around the loop here. Your thumb points in the direction of not only the dipole's magnetic moment, but also the magnetic field that the dipole produces. Okay, now here's an example. We have a circular coil of wire that carries 50 amps of current. It has 50 turns in the area of 2 square centimeters. It is placed into a magnetic field of 0.30 Tesla. It's oriented so the field is parallel to the plane of the coil. What torque acts on the coil and what happens to torque if the coil is rotated? The physics of this is a coil and magnetic field. The coil is oriented so that its normal and its magnetic moment mu, which is the green arrow here, is perpendicular to the field. So the torque will be a maximum. In other words, this is rotated so that this is over here. The knowns of this is the current is 50 amps. The area is 0.0002 square meters. And by the way, I've seen a lot of people having problems with their homework because they aren't converting to SI units or doing proper units cancellations. If you don't do units cancellations and convert to SI in this class, your grade will be terrible. And I've seen that happening. So those of you who are forgetting to do units, okay, fix that bad habit because it's not going to do you any good. The number of turns is 50, that's N. B equals 0.30 Tesla, and theta is 90 degrees. That's this angle here. Okay, we saw this. The torque is NAIB sine theta, or 50 turns times the area of 0.0002 square meters times the current of 50 amps times 0.30 Tesla for the magnetic field times the sine of 90 degrees. This is a maximum torque, so it's 0.15 Newton meters. Since the torque is a maximum, any rotation, which would occur naturally the loop is free to move, would reduce the torque. The loop would rotate until it encloses the maximum number of magnetic field lines and until mu is parallel to B. So in other words, this green line here will line up with B. Now here's some of the right-hand rules. There are many, many variations on these. I'm not going to go over these because frankly, you should be doing that yourself. And you should find out what works for you and write it down and use it. So these are the right-hand rules in this particular chapter. The direction of the magnetic field in a solenoid or current loop. You grab the solenoid with the fingers pointed in the current direction in the windings. In other words, your thumb is going to be pointing to the right here. Okay? So that will be the magnetic field's direction. Now, it's pretty much the same right-hand rule for the magnetic moment of the loop or coil, because the magnetic moment of the loop or coil is in the same direction as the magnetic field generated by the loop or coil. So in other words, you point the fingers in the direction of the current around the loop or coil. Your thumb points in mu's direction, also B's direction. Ampere's law, to determine the positive direction for the current, curl the fingers of your right hand around the loop in the direction you choose to thumb. Your thumb points in direction for positive current. Okay, if the currents in these wires have the same magnitude but opposite directions as shown, in what is the direction of the magnetic field at point P? Hint, find the direction of the field from each wire alone and add them to the principle of superposition. It turns out it's direction 3. So we're going to use the right-hand rule. We can sketch the magnetic fields due to the two currents. Adding them up in vectors, visually in vectors, gives the total magnetic field, and it's pointing downward. So in other words, we have this one. It's going away from you into the page, so you put your thumb into the page here. The magnetic field is along this line right here, this curl right here. This one, you have the thumb coming at you out of the page. Your fingers curl in this direction. The sum of these two curls at this point is down the page, which is direction number 3. Each of the wires in the figure below carries the same current either into or out of the page, in which case is the magnetic field at the center of the square the greatest. Now, it turns out it's arrangement number 2. Now, I only drew some of these because otherwise it gets really confusing. All of the other ones cancel, so the magnetic field is 0 at the center. Use the right-hand rule to find the magnetic field from each wire at the center. Add them up as vectors. Okay, so I picked the two that are opposite to each other across the corners of the square, because you're interested in the center of the square. So these two are the ones that are going to interact at the center of the square. Now, I first tried both of them going away from me. Thumb into the page, and my fingers curl for this one in this direction. I put the thumb into the page here, my fingers curl in that direction. Notice they cancel out. So these two cancel out. I did the same thing with these two. They're coming at me out of the page. When I did that, my thumb's coming out of the page, my fingers are curling in this direction for this one. My thumb's coming out of the page, my fingers are curling that one in that direction. So in other words, if they're moving, if the currents are in the same direction across the corner of the square, they cancel. Doesn't matter whether it's going into the page or coming out of the page, they cancel. Now, the other type of situation here is if they're across the square and they're going opposite directions. And that is the one where they add up. So in other words, I took this one and this one. The thumb is coming at me out of the page for this one, so the fingers are curling this way. This one, the thumb is going into the page, and the fingers are curling that way. So these two are adding direct together, and their net is somewhere in this direction. Okay, so and then I looked at these two, and I'm beginning to guess that they're going to add too. This one is the thumb's coming out at me out of the page, so the fingers are curling that way. This one, the thumb is going away from me into the page. The fingers are also curling this way. So these two are going this way. The total field is in that direction toward the left. So this one is arrangement number 2. This is the only one that will have anything. All the rest of them cancel out. Okay, positive charge moves parallel to a wire. The wire and the charge are both in the plane of the page. If the current is suddenly turned on, in which direction will this force on the charge act? Well, there's 2 ways to do this. The easy way and the hard way. The hard way is use the right-hand rule to determine the magnetic field produced by the wire. You grab the wire with your thumb in the direction of the current. If you do that, you find out the magnetic field is pointing at you at the point Q here, where this charge is. Then you use your other right-hand rule for a moving charge in a magnetic field. Magnetic finger, which is your middle finger, should be pointing at you out of the point where Q is. Your index finger, because it's a positive charge and it's right hand, is going up the page. The thumb points toward the right here, so these two are going to be attracted to each other. So it's going to be moving in the positive X direction. The other way is to realize that this is a current moving in the positive Y direction, and so is that. And parallel currents attract. So this is going to get pulled toward that one. So it's going to be pulled toward the positive X direction. There's always 2 ways of doing, or almost always 2 ways of doing right-hand rules. And you should apply both ways because they usually back each other up. If they don't, you might have done something wrong. So you might want to check on that. Okay, 2 straight wires run parallel to each other, each carrying a current in the direction shown below. The 2 wires experience a force in which direction? Well, parallel currents attract, so they're going to be attracting toward each other. Now, if one of the currents is reversed, the forces are repulsive. In what direction is the magnetic field at the center, which is point P of the square of this loop of counterclockwise current? Well, there's also 2 ways to do this. It turns out it's out of the page. We can use the right-hand rule for each wire segment or the one for finding a magnetic field from a current-carrying loop. So in other words, if we use the right-hand rule for each wire segment, we'll start over here. So we have the current going up the page. Okay, we grab the wire with our thumb going up the page, the magnetic field at point P, your fingers are pointing at you out of the page. If you do the same thing here, you get the same thing. The current is going to the left here, your thumb's going to the left, your fingers at point P are pointing out of the page. If you keep on going around this thing, the fingers are always pointing at you out of the page. The other thing to do is to grab this whole thing with your hand, with your fingers pointing in the direction of the current. Your thumb points out of the page. So both of them end up pointing out of the page because they back each other up. If the current gets reversed, the magnetic field is also reversed, and the magnetic field points into the page. 2 parallel wires have currents that are in the same direction but differing magnitude. The current in wire A is I, the current in wire B is 2I. Which of the following statements concerning this situation is true? Well, you can't forget Newton's third law. The wires will attract each other with the same amount of force. The drawing shows 2 long, thin wires that carry currents in the positive Z direction. Both wires are parallel to the Z-axis. The 50-amp wire is in the XZ plane, so here, and it's 5 meters from the Z-axis. The 40-amp wire is in the YZ plane and is 4 meters from the Z-axis. What is the magnitude of the magnetic field at the origin? Well, the first thing I did was I oriented this to look down on it from above. So I'm looking down on the Z-axis, and the 40 amp wire, the current is coming at me, up toward me, okay, and it's 4 meters away. I take my thumb, point it at me, out of the page, and my fingers curl this way. So they are going down the x-axis in the direction of positive x. Similarly, this current is coming at me out of the page, and my thumb coming at me out of the page. So now the magnetic field from this particular 50 amp one curls in this direction. It goes along, at this point, it goes along the negative y-axis toward the negative y-axis. So, and the sum of these is going to be somewhere here. Okay, and it turns out to be item C, which is 3 times 10 to the minus 6 Tesla. At the origin, the magnetic field from the 40 amp current will be in the positive x direction, and that from the 50 amp current will be in the negative y direction. Since these are perpendicular, we can use the square root of the sum of the squares to get the magnitude of the combined field. But we still need the magnitude of each one. So we're going to say B equals mu naught I divided by 2 pi r, or 2 times 10 to the minus 7 Tesla meter per amp divided by I times r. Now we canceled out the 2 pi from mu naught to get rid of that. Whenever you have to compare anything in a problem or do something like that, get rid of the constants, okay? Take care of things like this 2 pi and the mu naught. Okay, so simplify it. So for B for the 40 amp, it is 2 times 10 to the minus 7 Tesla meter per amp times 40 amps divided by 4. That is 2 times 10 to the minus 6 Tesla. Notice that the 40 amp divided by 4 meters is 10 amp per meter. And 50 amps divided by 5 meters is also 10 amp per meter. So these two have the same magnitude. If they have the same magnitude, they're going to be at a 45-degree angle here. And you can just take the 1.41 times one of them, the square root of 2 times one of them. So it's 1.4 times 2, which is 2.8 times 10 to the minus 6 Tesla, and the angle will be 45 degrees. A solenoid of length 0.250 meters and radius 0.0200 meters is comprised of 120 turns of wire. Determine the magnitude of the magnetic field at the center of the solenoid when it carries a current of 15 amps. B equals 4 pi times 10 to the minus 7th times the current times n divided by the length of the solenoid, or 4 pi times 10 to the minus 7th Tesla meter per amp times 15 amps times 120 turns divided by 0.25 meters. It is 9.05 times 10 to the minus 3 Tesla. A portion of a loop of wire passes between the poles of a magnet as shown. We are viewing the circuit from above. When the switch is closed and a current passes through the circuit, what is the movement of any of the wire between the poles of the magnet? Now, what I always do is I look at the situation from the standpoint, is the current perpendicular to the magnetic field? If the current is not in some way perpendicular to the magnetic field, if it's parallel, nothing's going to happen. Now, this is perpendicular, so definitely something's going to happen. Now we just have to determine what is going to happen. Okay, now it's going to move perpendicular to both the magnetic field and direction of the current. So it's not going to move toward the north or south pole of the magnet. It has to move either upward or downward. So we have to decide which one. At this point, we have to decide what is the direction of the current. So we take the direction of the current, and it ends up going from the positive plate around here to the negative plate. So the direction of the current is down here. So the index, of course, is down the page. The index finger is the direction of the current is down the page. The magnetic field is going to be pointing from the north pole of the magnet to the south pole of the magnet. Your middle finger is going to be pointing to the left. Your thumb, which is the force, the thrust, is into the page. So it's going to be moving downward into the page away from us. This one's a trick question. A wire connected to a battery and a switch passes through the center of a long current-carrying solenoid as shown in the drawing. When the switch is closed and there's current in the wire, what happens to the portion of the wire that runs inside the solenoid? Okay, well, the magnetic field in the solenoid goes down the center of the solenoid. The current in the wire is running parallel to the magnetic field. That means there's going to be no effect at all. There's no force. Thank you.